Hello everyone, this is Professor Gates here with a short video for you about amount and rate functions and their relationship to the derivative. There will be a short assignment on Edfinity after this with a couple multiple choice questions, and I just wanted to give the disclaimer that you only have 2 tries instead of infinitely many tries because there are only 4 options, and so hopefully 2 is enough. Alright, let's go ahead and get started. Alright, so let's go ahead and talk about what an amount or rate function is first. So for us, we'll have some starting function called f of x. Usually this will be our amount function. So a few examples. Right, so it could be cost, population, of a community, of anything. Your position, with respect to a starting point. You could say how many miles east are you of your starting point, and track it where x is time. Any of these are reasonable examples. And then we're going to have f prime. So this is going to be our rate function. In calculus, we call this the derivative. So why is it called a rate function? Well, the derivative is actually the instantaneous rate of change of the amount function. So what do we mean by instantaneous? So this just means like at that specific moment in time, right? So in terms of position, you're talking about velocity at a certain second. Population, how is it growing at that exact second, not over a 10-year period or something like that. Okay, so looking at our examples above, let's translate them into the rate functions. So the rate of change of cost is marginal cost. We would then talk about like the growth or decay of a population. A population could be decreasing. And for position, the instantaneous rate of change is velocity. All right, and that's going to be the example that we focus on in this video. So the first thing I want to talk about in terms of velocity is why we choose the terms position and velocity instead of distance and speed, and actually distinguishing between these things. So if you think about when you're talking to someone about how far you've gone, you never say, I went negative miles, right? A distance traveled is always non-negative. Same with speed, right? You read your odometer, it does not have negative numbers on it. So that is what distance and speed is talking about. It's always non-negative. On the other hand, position and velocity give us a bit more information, right? These tell us about direction. So you notice in my example, I talked about like miles east of something. Well, if you go west of it, you are negative miles east. Same with velocity. If you are going backwards, then you have a negative velocity, but a positive speed. Another example would be something like falling off a cliff, right? You're traveling at, probably a very fast speed, but a negative velocity because you are traveling towards the ground and not up toward the sky because gravity. So then how do these two correspond to one another? Well, if your position is increasing, then this would mean what about your velocity? Well, you are having a positive rate of change if you are increasing, and so your velocity would be positive. And then the opposite would also be true. If position is decreasing, then velocity is negative, and vice versa. We can even take this a bit further with acceleration. So velocity is the derivative or the rate of change of position. And of course, you might see this in something like position in meters, velocity in like meters per second or something like that. And then the derivative of that, which if you have a second derivative, it would be written f double prime here of x. The derivative of the derivative is acceleration, right? Because this is going to be something that is written as meters per second squared, which how can you really think of that? Well, it's meters per second, or the rate of change of the velocity over time. All right, so let's do an example. Here we have a position function, so I'm keeping track of the position east of home. Let's just say we're going on a nice little drive, and our time is in hours. So our goal will be to get our velocity function, the graph of it, from this graph. Okay, so our velocity graph is going to be down below. So the first thing that we should notice is that our position, we start off traveling east, right? We are increasing our distance east of home up until around 4. So since the distance is increasing, or position is increasing, our velocity should be positive. And then how exactly should this look? Well, it should be fairly close to constant as we start, right? Because we're increasing at a pretty steady rate here. And so maybe, it's up here, it's positive, it's fairly steady, and then, say around whatever, 3 here, it starts tapering off. We're no longer increasing quite as fast, but we're still increasing until we hit 4. And so we taper off here. Our velocity is not quite as high, but it's still positive. And then at 4, we stop increasing. So we're going to go ahead and hit 0 here with our velocity. And then we start going west of home, right? And so our position is decreasing, so our velocity should become negative. It starts tapering off pretty slowly, so it's not too negative, but then it hits a pretty constant rate, and it's somewhat steep, so it kind of increases here. Through 8, right, we keep decreasing through 8 all the way until, we hit 10. And again, we're kind of tapering off here around maybe 9, where we're no longer decreasing quite as quickly, so we're going to come back up as we hit between 9 and 10. And then again, 10, we've now hit our valley, just like our peak at 4. Our velocity is going to be 0. We stop decreasing, and we start increasing our position again as we turn back towards home. And so we're going to be positive again as we finish up. Okay? And so again, that was all just interpreting this as the rate of change of the graph above and kind of tracking what happens. Okay, so here's the first exercise. So you'll actually find the problem on Edfinity. It's going to be multiple choice, and I want you to choose the correct velocity graph corresponding to the position graph that I've graphed below. Obviously not necessarily to scale, but yeah. Okay, so the last thing I want to discuss is average velocity and kind of its relationship with instantaneous velocity. So let's recall. So average velocity is your change in position over your change in time, right? So your final position minus your initial position is your displacement or change in position, and final time minus initial time is the change in time or the time elapsed. So how is this different from instantaneous velocity? Well, let's think of a couple examples. So let's just say you're having horrible traffic on your way to Indianapolis area. You're driving 50 miles. It takes you 2 hours. Well, your average velocity is pretty simple to calculate. It's just going to be, your 50 miles that you traveled minus your 0 starting because you hadn't traveled at all at the start over 2 also minus 0. And so you average 25 miles per hour, right? It's pretty simple. But your instantaneous velocity, right, like you're probably going very different speeds throughout this. You're not going a consistent 25 miles an hour necessarily. So at any given moment, you could be going, 80 miles an hour for a bit, and then suddenly you're going 0 miles an hour because you're just, parked on the highway. So that's one difference between the two. Okay, so let's say we had a round trip instead. So, we had some tough traffic on the way out, but on the way back, it only took 1 hour. Not too terrible. So what's our average velocity? Well, we traveled 100 miles round trip, but our change in position is not 100 miles, right? So our position is actually staying the same at the end, right? We started at home, we went out for a bit, went farther away, and then we came back, and we're back where we started. So our initial position is 0, and our final position is 0. So we actually have no change in position, and of course there is a change in time, but 0 over 3 is 0, and so our average velocity is 0 miles per hour. But what about instantaneous velocity? Well, obviously if we traveled 100 miles, we had to be going at a speed above 0 for this whole time. But our velocity, well, as we leave and go to Indy, we're going to be increasing our position, right, away from home. And so our velocity will be greater than 0 or positive. And as we come back, our position is getting closer to home, it's decreasing. And so coming back home, our velocity, our instantaneous velocity, will be negative. All right, so I'm going to close this with one more exercise. It'll be on Edfinity, and then that'll be all. All right, so Eliud Kipchoge, so he's the Kenyan world record holder in the marathon. Let's just say he's out for a workout, running 22 miles straight out along a trail, so in one direction, in 100 minutes. And then once he's done with that, he turns around and jogs back the way he came on his cool down for 3 miles in 20 minutes. I want you to find his average velocity for the entire run in miles per hour. Okay? Thank you for watching.